So, welcome again. Today, I wanted to spend a bit of time clarifying maybe things from the first lecture and doing sort of a reminder. And then especially spending time on the second half of, the last 20 minutes of the lecture that I went very fast because I saw I didn't have time, so I went faster, and then it doesn't help with making things clearer as I learned. So the plan for today is basically a little bit more on clarifying the language definitions that we're going to use to compose those modules. But before that, I had a few questions about the definition of weak simulation, and that I think is important that you understood. So I mentioned that a weak simulation is a relation in which first you have a base case in which the reset state of your two machines are in the relation. So here you have M0 and M prime 0 as related by phi. But it has to be the case that phi is inductive by all the transition of the system. So you remember that for all action methods that I take on my implementation side, I can take a step on my specification side, potentially followed by some rules, which are internal transitions. And it has to be the case that after I do all that steps, I am still in the relation. And same thing for the rules. I didn't show the diagram because it's the same for the internal rules of the system. But the important thing, which I thought I said, but maybe I didn't say it clearly, is the fact that phi implies a form of indistinguishability. That is, if you have two elements that are related by the relation phi, then necessarily they are observationally indistinguishable. That is, for all value method, if you were to try to see through the value method, the value returned by the value method, and you would get a value ret, then it has to be the case that if you were trying to call the same observation method from the specification, you would see the same value, okay? And once you have all of that, then you have this notion of weak simulation, and you have the theorems that I mentioned that if two machines are weakly related, one is weakly simulating another one, then the set of traces of that machine is included in the set of traces of the other one. Okay? Yes? You say that the formula is missing a equal ret. Is it your question? Yeah. Okay. Yes. Okay. So first, so that was just a little clarification. I wanted to write down the language, and yesterday I was sort of still hesitating. So should I go with the purely functional presentation, or should I go with the imperative presentation? And I sort of did a mix of both of them simultaneously. So I talked to Arvin this morning. I said, what should I do? Should I go with the pure functional one or the imperative one? And he said, well, you should go with the imperative one, because that's the one that they're going to use if they do any experiments in BlueSpec. So the concrete syntax in BlueSpec looks like something like this. So don't look at what is below. I had to draw some amount of circuitry for later, but you can ignore that. So we are going to have two kinds of grammatical construct. We have expressions. And expressions are basically composing observations, right? So it's calling a value method, and it's then applying a pure function to value method. And then we have statements, and those are the things that are going to change the state of the system. And well, you have the sequence. You have the conditional, where the conditional can only depend, obviously, on an expression. And then you can call an action method, which is fundamentally a little bit like setting a reference, updating the submodule. And then you can give a name to a sub-expression, which is actually useful, and semantically it's important. And then you can abort, say that this is a case where the relation is partial and it's guarded. Okay? Okay. So the goal of today's lecture is mainly to explain how, if we have a set of modules, and those modules are a piece of hardware, and we have models for them as well, then if we write any program from that syntax, which is well-typed, even though the type system is not written here, then we can actually write a piece of combinational logic, a piece of hardware that is gluing together all the submodules by being faithful to the semantics of the language, which is sort of self-describing here. Okay? And I will try to show you that there is a fundamental problem when you do hardware that is related to the concurrency of the underlying system. And I want to start this by sort of showing you a very simple representation. So yesterday I did tell you something which I think was clear, was that we are going to encode the notion of method call through a sort of handshaking in circuit, where there will be a ready signal that tells us, is it the case that I can call that method, which is it the case that the relation is not partial? And then we are going to have an enable to say, I want to actually call that method, okay? And the simplest kind of systems that we have in hardware is just a register. And in a register, you could really think of it like it has two methods, one write method and one read method. It turned out that those systems are so simple that the ready is always 1 for write. It's always ready for it to write to it. And the ready for reading the value is also 1 too. You can write a new value by setting the enable to 1 and by putting some value on the wires. And then you can read the value inside the register by simply looking at the wire here. And whenever you write, and that's a peculiarity of hardware, everything is synchronous. That is, if I were to look at a timeline, there is this notion of clock cycle. Everything is clocked by a clock cycle that you've probably seen in class, in your undergrad. And basically, if I were to write at this time, the value would only be seen next cycle. That is, if I write 42 to the register, and I try to read the same cycle as the register, I don't see 42. I only see 42 the next cycle, okay? And that's gonna be a problem. Why is it gonna be a problem? Because in my language, if I write a program that looks like, hey, I have a register, and I try to write to it 42, and then, you know, oh, I do a let e equal r.read, then this is not gonna have the behavior that you're expecting by the semantics of, you know, semicolon of composition, because if I just try to look at the value that is on the wire of read, I'm not gonna see the value that was just written, I'm gonna see the old value, okay? So in a sense, if I think of this program and I give it a sequential semantics, I will not be able to compile this program to hardware because I will not be able to observe the new value out of the register, okay? So there is this fundamental problem that even though we can sort of encode the notion of handshaking, we still need to face the problem that if we have a role or a method that calls multiple submethods of submodules, what happens with the simultaneity? What happens if it's calling two methods of a submodule? And maybe those two methods, when you call them simultaneously, they don't behave like the order in which you call them, or maybe it's even forbidden to call them simultaneously. Let me show you an example where it is actually forbidden to call them simultaneously. So here, I came up with a weird counter example. It's a simple module, and it has two methods, increment by 1 and increment by 2. And I gave two possible circuit implementation of that little machinery. And they have the same interface, but I want to show you that one of them can do really weird thing if you're not careful with it. So let's actually start by this version because it may be the simplest. In that version, I just put a register inside my module. And what I do is I say, well, you know, I'm going to hook up that wire to a first thing where I'm going to say, sometimes I need to apply 1 to it. Sometimes I don't do anything to it. And that's selected depending on, do I want to increment by 1 or not? So at this point in state, my signal basically represents either the old value or the old value plus 1, depending on if the enable is high or not, okay? And then I make the data flow through a second of this forking system, in which I say, based on the second increments, I'm gonna select, do I want to add on top of that? Do I want to add 2, or do I not want to add 2 to it? And then that's the new values that I'm going to write back to the registers, okay? If I think about what this system does when I call simultaneously increment 1 and increment 2, then conceptually what it's doing is that it first increment by 1 and then it increment by 2, okay? It happens to be the case that actually addition is commutative, so it doesn't really matter in which order I do them, but it looks like if I were to set those two wires, the behavior of what's happening in my module is basically doing sequentially increment by 1 and increment by 2. Okay? Is that clear? Okay. Now, I could have a slightly different piece of hardware in which what I say is, actually, I will never want to be able to simultaneously increment by 1 and by 2 because that's just my context. I know that, and I can do a better circuit. And so the problem with that circuit is that there is a very long critical path that is to be able to look the times that the signal needs to travel here. It has to go through 1 and through 2 in the worst case, which means that if I wanted to clock that circuit, it would be quite slow. In this circuit, I never go sequentially to 1 and 2 simultaneously. if you look, I either go through 1 or through 2. So conceptually, it's a faster clocked circuit. But the way you look at it is that if, by mistake, I were to call both increment 1 and increment 2 simultaneously, then I would get garbage. Because the circuit I would get here is basically, would just get garbage. It will not mean anything, okay? So there is this notion that whenever I have a circuit and I have a bunch of ready enables that correspond to methods, I need to worry about a bunch of things. The first thing I need to worry about is, like, does it make any sense? Can I call 2 of the sub-methods of my module simultaneously or not? And if I can call them simultaneously, what is the meaning of calling them simultaneously? Is it the case that it's as if I had done method 1 and then method 2? Is it the case it's as if I had done method 2 and then method 1? Or is it actually a diamond property where they actually commute, and we would say in that situation that they are conflict-free? Does that make some sense? Okay, so the very important construction that we're always going to have is the notion of a conflict matrix. And the notion of a conflict matrix is simply going to say we're going to look at pairwise set of methods, and we're going to characterize where is it in terms of ordering. So we define the conflict matrix, Cn. Oops, this one is not so good. Yes. So the conflict matrix of a module is something that basically defines for every pair of method, both action value and action method and value method, what happens if I were to do both of those methods simultaneously. So for a register, for example, I have 2 methods. I have write and I have read. I have write and I have read. And basically, I need to wonder what would happen if I would do write and write simultaneously. It doesn't make any sense. I cannot double write in a register, right? I can only write one value to a register. So I should never allow myself that if I have a piece of my program which does something like m.write 42 and m.write 12, in terms of hardware, this is ill-defined. In terms of sequential composition, it's, well, if you write 12 at the end, but in terms of hardware, that's sort of a double write. You can't write 2 values. So you cannot double write, so we say that it's conflicting. And if I ever reach a program which does something like this, I'm going to throw my hand and say, sorry, you wrote the wrong program. You're not writing hardware here, okay? So here, all those things I'm doing are basically a set of restrictions that are going to bubble up to the language. And when I'm going to write my program, there is going to be a bunch of static analysis that guarantees that the constraint coming from the conflict matrix of the submodules are enforced and make sense in my top level, in my program. Yes?
I guess specifically for registers, how do we know when writing twice is okay? Because you want to probably rewrite over the same thing.
So here I am talking within one rule. So within one cycle. So you will be able to rewrite to that register next clock cycle, but not within one rule. Because one rule is atomic, an atomic action, like we remembered, we learned. And yes, there was another question?
Oh no, I was just
yes, so I need to repeat the question, but I forgot the question, so I can't repeat the question. Yes, the question was, how do you know when you can write? Because at some point you should be able to rewrite to the register, and the question is like, you cannot write twice in the same cycle, but across cycle you can. Yes?
Why not have a semantics where the second write will dominate the first write?
Yes, so that's actually possible, and that's actually what's done by default in the BlueSpec compiler, but Arvin doesn't like it, and I don't like it neither. But so you are in this very specific case of a register, you can actually do an optimization in your compilers. Yes, and I need to repeat your question. The question was, why don't you do a semantics for write in which the second one overtakes the first one, and you just encode that? And the answer you just heard, so I don't need to repeat. Yes?
Is this conflict matrix described explicitly by the programmer, or is it inferred by?
No, it's going to be inferred. The only ones that, so yeah, let me keep going. Okay. So what happens if I do a read and a write simultaneously? Well, the write happens after the read, that's what we said. What happens if I do a read and a write simultaneously? Well, the matrix is going to be anti-symmetric, or this. And then what happens if I do 2 read? Well, I can absolutely do as many reads as I want, because there is nothing, that just commutes, it's just an observation. So we call that conflict-free, okay? And to answer, so to repeat the question first, someone asked, are we going to have to write this conflict matrix, or is it going to be inferred? And the answer is going to be, for your base modules, they are basically have to be specified by hand. But then every single program that you're going to write in that language, it's going to be inferred from the conflict matrix of the subprogram, what's the conflict matrix of the bigger program.
May I ask a follow-up?
Yes, but after your neighbor. Yes.
Why is it allowed to do write and read in the same cycle?
Yes, very good question. So what happens if I, you need to think in terms of sequential semantics. If I both write 12, so that's a data wire, and I also set 1 for the enable, and I call the read method, I will observe what was inside the register before. So it will look like, if I think in terms of sequence of events that happens, it will look like I first call this method, which is the read one, and it did return the 42, that was the old value, and then I called the write method, which happened to update. Okay? Yes?
Sure. How do we map this sort of understanding to the microarchitectural state versus the ISO state?
Let me delay that question. Okay? But that's a good question. Good? Okay. So now you understand that basically when we compile, we are going to spend most of our time rejecting program. We're going to say, no, that's not a good program. Sorry, you wrote something that doesn't make any sense for me. But if it happened to be the case that the program you wrote verify all the constraints corresponding to the conflict matrix, then we can compile it because we will just have to define as an expression, as a combinational expression, what is, and that's what I very briefly said yesterday, oops, what is the, how to define the output of the system. So here the output is data.read, and here, and also data.write, and also enable.write. How do I write what is the value of those expressions as a function of all the other signals which are input to the system? Okay? And if I know that the sequential, the parallel composition of the submodules as a semantics which correspond to some conflict matrix, then if I just wire things together, it will have the right semantics because we just made sure we rejected everything that would not have the right semantic. Does it make sense? Okay, so I just want to tell you a little bit how to compile a little bit more concretely, but not in great detail neither, because I want to have a bit of time after that for giving you an example of weak simulations, because I didn't do that yesterday. So, now, there is one problem with that language, basically, and the problem with that language is this. You see, intuitively, if you don't have conditionals, then the problem is fairly straightforward, because what you have is basically a set of statements that correspond to what should be all the ways in which you update, in which you call the method of the submodule. So first, let me explain to you how to compile to circuit a program in which there is no if in your syntax, and then I will explain how to get rid of the ifs, okay? So compilation without if. And the compilation goes into 2 steps. I first need to sort of say, actually even 3 steps. First step is to say, okay, every rule and every method, one by one, I'm going to have to say what is that method trying to do to all the submodules, and how does it want to update to the effect of all the submodules. So that's the first thing I need to do. Then I need to say, once I have basically compiled individually every single piece of my system, how do I compose all the rules and all the methods into one circuit? And then I need to explain what is the conflict matrix for that new module that I built. Okay? So let me first explain how do I compile one rule or method, it's the same thing, that does not contain any conditional. So you can basically think of it like it's once you have flattened the whole thing, it's just a sequence. So first there is a question we can ask is there abort in my program or is there not abort in my program? If there is abort in my program, it's very easy to compile my program because my program does nothing. Okay? Because if I don't have an if, then I can really think of my program simply as a sequence of call to the action method of my system with or without at least one abort. So in the case where I just have calls to methods, right, m.a1, m1, m.a2, am2, so on and so forth. So it's basically a regular expression for a bunch of things like this, and then maybe an abort. In the case where there is an abort, it's very easy. I have nothing to do because that program does nothing. So let's consider the case where I just have a set of method calls, okay? And this set of method calls, I just perform inlining of all the variables which are in the system because they're just easier to do like this, okay? And then what I'm going to do is I'm simply going to look at, I have many action methods, and I'm going to say, is it the case that I ever repeat twice an action method in a situation where there was a conflict for that action method with itself, right? So I'm basically going to go through that sequence and look at, is it violating the conflict matrix in any way? Does that make sense? If it's violating the conflict matrix, for example, if in that sequence I turn out that I have module.write twice, I'm going to say, sorry, I cannot compile that program. This is an invalid program. So I reject every program in which, if there is twice repeated, if there is a set of two action methods which are conflicting with, with each other. Okay? So now I just keep all the, I just reject all programs that don't verify that thing. So now I have a program that does verify that property. And then I'm simply saying that, well, I'm going to define that enable for all the methods that are here are going to be 1. So let's consider first. So let me, so I will do the case in which we have, let's say, 3. It's going to be, I'm going to do an example in which we have 3 methods, and then you're going to generalize this to n methods, because I think it's basically the same thing. So am1 of some expression, maybe you have twice the same module, and then you have another module. am2, m prime, and let's call it E1, E2, E3. Okay? So the first thing I can do is to say, what is, so this, let's call it the rule R. And I need to decide 2 things. I need to say, what is ready of R? When is it the case that a rule is ready? And when is it the case that an action method is ready? And then I need to explain what are all the signals for the different method of the submodules, which is what are the enables and the data that correspond to the submodules. So I need to give you that, and I need to give you the enable for m_am1, and I need to give you the data for m_am1. And then I need to give you the enable for m_am. That was another one. am2, am3, 2. And then I need to give you the data for this one as well. And then I need to give you the enable and the data for m prime of am3. And then the data. Why am I doing that? 2? So if I can give you a closed expression for all those signals, just as a bunch of and or not and simply combinational function, that's exactly connecting the wires as I was describing, because I basically specify the system of the full system. And all my expression, what can they depend on? They can depend on the output of the submodules M, and they can depend on the enable of the role, which is an input to the system. Okay? So I'm saying, if I want to do the rule R, how should I set the enable of the different module, and how should I set the data of the different module? Okay? That's going to be very easy. Why is that? Well, first, when is it the case that R is ready? Well, yes? No? Yeah, okay. R is ready when all of its elements are ready. When all the methods that you are trying to call are ready, then R is ready to go. Well, so that's easy. It's going to be a big N. I guess we can write it like a big N of all the ready signals for all the submodules which are called in my program. Okay? So all the action methods, all the value method which might be in the E1 and E2 inside. I take all those signals and just end them, and I say the only way in which I could ever do R is if all of them are ready to go. Okay? And then I'm saying, how do I define the fact that I am indeed desiring to do AM1? Well, it has to be the case that it's simply enable of R, because you only will update A1 if you want to do R. And then, how do I set the data? Well, it's basically going to be the compilation of E. That is, I'm going to look at the value produced by E, and I'm just going to put it here. E. And because E is just a pure value method, it's just combinational, and I just look at the output of the method, and then I make it go through the different functions, and I just wire it, and then I put it here. Okay, so I'm going to note that translation of E. Okay? And I can do everything for everything else, and I just have a very simple way to say, if I had a system with a single rule, that will be a very good way to compile that system. Okay? A single rule with no conditionals. Does that make sense? Okay, so now the problem is that I have conditionals, and I have more than one rules. So how do I deal with having conditionals? Well, actually, conditionals are not too bad. Why are they not too bad? Because when you have a conditional, you can split it. You can say, well, it's as if I had two systems. I have a system in which E is true. So let me do a little rewrite. So let's say that I have a rule R, and that rule R has a conditional somewhere. Let's say, let's consider the first conditional in the system. And then I have a sub-expression little r1. And then I have a sub-expression little r2. And for the sake of argument, let's assume that r1 and r2 are if free. They don't have conditionals inside. Well, then I can basically say, is that not so different from having a set of two rules, one in which I have r1 followed by nothing, and one in which I have r2 followed by nothing. Maybe I have actually, to make it slightly more complicated, I will put an r3 here, and I will put an r3 here, an r3 here. And then I need to remember somehow that this rule only makes sense in the case where this condition holds, and that this rule only makes sense in the case where the negation of this condition holds. Okay? But that's fairly easy. I'm just going to basically say, well, I'm remembering that it's under the condition. I'm adding a condition, E1, and I'm adding a condition not E1. And then, so I keep that in my context. And then, when I'm writing my business here, I'm going to add an end with the condition corresponding to the thing. And then I know that I'm going to select just the one that I care about. Yes?
I don't want you to trip, but it looks like you're shooting.
Yes, I think that's a very common thing, but thank you. I could trip, but that's a good one.
Jumping around a lot.
Yes.
I was a little worried.
Okay. So you basically just remember what's the condition, and then you have two subproblems. You know to compile the two subproblems, and you know how to merge them, because the way you can simply merge them is by basically guarding that either you do one or you do the other. Okay? Does it make some amount of sense? I don't want to get too much into detail, but I want to give you an idea that you can basically get rid of conditionals systematically. And you can do that recursively, and you can flatten everything, and so on and so forth. Okay? Actually, there's multiple ways to compile, but that's what you can think of that as a strategy called split ifs, where you just say, well, you know, when you have ifs, it's as if you didn't have if, but you have more rules, and that makes it easy. Okay. So I told you how to compile one rule or one action method, because one action method is going to be the same. Value methods are very easy because you don't need to do anything. Only thing that you need to do, it's a pure function, so you basically just need to hook up. So if I look at the body, so when you define a value method, the definition of a value method is going to be an expression in the language. And so it's basically just going to be a bunch of combinational functions that at the leaves have sub-value methods. So you can just, you know, let the value returned by the value method go through the data flow of the pure functions. And then you have your compilation for your value method. And then for the guard, you basically do the ready of all the guards that correspond to this. Okay? Does that make some sense? Am I going too fast on that, or is it okay? Okay, let's assume it's okay. So, so that's basically the single rule, single method, single value method case. And now, what do I want to write? I want to keep that one. So maybe I want to keep that one. I don't want to keep that one. So now I want to explain two related problems. One related problem is going to be, the first part of the problem is going to be how to merge two rules simultaneously. And the second problem is going to be how to compute the conflict matrix. And the reason why they're going to be related is because we are first going to compute the conflict matrix that's going to tell us how to merge rules. So let's do an example, because I think that an example is going to be the easiest way to understand. So let's assume that I have a first rule, R1, and I have a second rule, R2, and their body is like this. One is reading a register A, so let's call that the X value, and A.read. And then it's writing the value that it just read to the B register. Okay? And then the other rule is doing sort of the symmetric case in which it's reading B, but then it's writing A with the values that it just read. Okay? And it's very easy to write circuits, because I just explained to you how to do it for that rule in isolation. It's very easy to do it for that rule in isolation. There is not even a problem with ifs. But now the question is, if I have a system of those two rules, how do I compose them together? And the first question that we are going to ask is, we are going to say, well, first, this program is legal because you read before you write, and there is no problem there. Just a small parenthesis, in BlueSpec, actually, there is a way in which even if you read before you write, it automatically leaves the read before the write to make it less painful. But let's ignore that little technical details. So here, the conflict inside the rules, there is none of them, because you're reading and then you're writing. So that's no problem. Here, same thing, you're reading and then you're writing. Okay? But if you think of the two rules with respect to each other, then you have a problem. Why do you have a problem? Because if you consider the submodule A, this rule is reading A, and this rule is writing A. So it means that when I analyze the fingerprints of the rules on A, I have that this rule must happen before that rule when I look at the sequential semantics. But when I look at B, they are doing exactly the opposite. That is, this one is reading B, but this one is writing B. So it means that the sequential semantics would say that it should be the case that this one occur before that one occur. And I think I reversed the two when I said that. That's, you understand the idea. Okay? But the problem is that I'm having contradictory information here. So it means that necessarily R1 cannot both happen before R2 and after R2. So it must be the case that they conflict. Okay? And so you can generalize this example in a very simple way. So you can build a little lattice. The little lattice is going to be the lattice of conflicts. So the lattice of conflicts. And what you're going to say is that like this. We have seen this lattice before, haha. And then you're going to say that you look at all the submodules and you lift the conflict corresponding to the submodules. And so you basically you are constructing the tuples of all the conflicts that you have in the submodules. So in this case, I have two submodules, A and B. And so I can construct, if I name this lattice L, I can construct some element of L to the K if I have K submodules corresponding to, for every submethod, what is the conflict on the submodules, okay? And then once I have this thing, so in this situation, it would have been on that module I'm requiring it's happening before, on this module I'm requiring it's happening after. And once you have computed that thing, you can simply squash it by saying that you must be compatible and go up the lattice by joining all the elements, and then you end up with a conflict here, okay? So I think that it's enough detail to explain how you can easily write a function that does this computation for you. Yes?
Yes, you have the rules and the conflicts. Is it just
it doesn't matter relatively what they happen with each other. So really what we are always clinging on is, actually I could have shown you what could have gone wrong. So this system of two rules, if I don't do the analysis realizing that they are conflicting, I could have done a naive thing in which I compile this thing, and then I juxtapose the two compositions as my new circuits. And if I do that, I would end up in a situation where the circuit that I generate doesn't have the properties that we call the one rule at a time properties, that is the next update of the system, cannot be explained in terms of a sequence of transitions which we had in your base system. Okay? So, so that basically tells you, oh, you can compute for every set of rules, every pair of rule and method and action method and stuff. What is the conflict, and can you actually do both of those things simultaneously? You didn't ask, but you could have asked, what about conditionals? And are you considering conditionals? How are you considering conditional, basically? So if we do the strategy of splitting ifs, then we could analyze for every pass of the conditional, how do they conflict? And that's what the compiler does if you do the split techniques. But you can also, and that's what's done by default, do a conservative analysis in which you say, well, you know, it doesn't matter. I'm going to conservatively say that two rules are conflicting, even though actually they are not always conflicting. And one good example of that would be to say, let's say that I add a little if here. I add if w.read is equal to 42. Then I write, but I don't always write. And then this analysis would be conservative if I consider that this is always written. And if I were to do a better conflict analysis, I would say, well, actually, sometimes it's conflicting, sometimes it's not conflicting. But then it becomes very complicated. Okay? Good. So now we have the conflict between every single pair of transition in our system as far as hardware synthesis is concerned. So the only thing we need to do is to basically decide. So notice that maybe between, so if I were to draw the whole matrix for the entire new system that I'm building, I might have many rows, and many of them might be not conflicting with each other. Oh, I have an interesting question for you. First, a little poll. Do you think that the relation is transitive? Do you think that if a first method conflicts with a second method, a first rule is smaller, it has to be scheduled before a second rule, and the second rule has to be scheduled before a third rule, does that necessarily mean that a first rule has to be scheduled before the third rule? No. I see yes and no simultaneously. Can we have an example why? Yes? Exactly. They could conflict on different memory cells. So it could be the case that the reason why R1 has to happen before R2 is because on register A, this one is reading while this one is writing. But then the reason why R2 is before R3 is because on register B, this one is reading and this one is writing. But maybe R1 and R3 have nothing in common, and then they don't have this problem. Okay? Which would be the case if we just, this one read A and this one write A and read B, and this one write B. Then this one touch B, this one touch A, but they don't touch anything in common, so they're going to be not conflicting. Okay? Slightly counterintuitive, the notation is misleading. That's just the way it is. Okay, so I was saying that you can, at the stage at which you have computed the conflict between every single pair of transition in your system, you might have a lot of freedom in what you want to do. So typically you will realize that you always conflict with yourself. And the reason why is because you have at least one person that is writing a register somewhere, and then once you consider that and itself, then it means that it's double writing, and then it's a conflict. But so on the diagonal, you will typically have conflict. But maybe you have, like, you know, a lot of conflict free. You are very lucky. Those R1 and R2 and R3 are not those R1 and R2 and R3. Those are new fresh names. And let's say that you are very lucky, and everyone is conflict free with each other. Now you have a problem. I guess it's not really a problem. You have choice. That is, in the way you do hardware, you will have the choice in the order in which you wire thing to decide what do you want to do. You might be over-constraining. You might be saying something like, this is not prescribing. You still need to pick a schedule in which order you want things to actually happen. That is, the system tells you it could happen either way. For me, it doesn't matter. But for your specific hardware OS that is deterministic, it will happen in one way. When it will happen in one way, you will need to basically fix the schedule. So the compiler does the analysis and then pick a schedule compatible with that set of constraints. So for example, here, every cycle, I would like R1, R2, and R3 to happen, let's say. And then I check, is that schedule compatible with this set of constraints? Well, it does look like it's compatible, so I could actually go with that. Now, if I had something in which I had R1 and R2 are conflicting with each other, then what would happen is that if I were to try this schedule, and I can try this schedule, it will never be the case that R2 happens, because I will first try R1, and when R1 succeeds and happens, then the compiler will realize that this would cause a conflict, so it will gate off the effect of R2, and it will say, I should never do R2 if I just did R1 before, and then it will go to R3. So you can think of this next phase of compilation that I'm describing right now as once you have compiled the conflict matrix, you need to write a piece of circuitry that is basically going through the rules of the schedule in sequence and trying these rules and making sure that if one of them can indeed fire, then it blocks everyone that would come after it that would conflict with it. Okay? And that would have an incompatible order with it. Okay? So basically, you take a schedule, you take a conflict matrix, and then you make sure that every cycle, what the circuit is going to do does not violate the conflict matrix. The same way that whenever we have compiled, we make sure that we have only compiled circuits that do not violate the conflict matrix. Okay? So how do we do that? That's not too hard. So I want to keep it here. Yes. Okay, so before I told you how to compute the enable. So when I have a rule R, I told you auto compute the contribution of R to all the enable and all the data of the system. Okay? So I told you, oh, I have enable of some module of some method, some action method, and I told you there is a way to compute that, and except that this was for the rule R, so I can think of it as just the contribution of R to the enable. Okay? Then I can do the same thing for all the signals, the contribution to data of R. And then I need to merge all those signals to get the real enable, which is once you consider that you want to do all the rules you want to do in the cycle, which of the rules should you actually pick? And which of the data signals should you pick? So you basically, if I have two rules, R1 and R2, with what I told you right now, you have a little trouble, because if both of them are using the same action method, and you have so created two enable, one coming from the compilation of R1 and one compilation from R2, then you need to say, well, what is the actual enable to the circuit? And the actual enable is going to depend on the schedule. So you're going to say, well, let's consider, for example, I want to compile with the schedule R1, then R2. And I noticed that actually R1 have to happen before R2, okay, in my conflict analysis. Well, if that's the case, then I can simply compile by saying, first, I need to get, is it the case that R1 is ready? So I'm going to compile the first thing, which is ready produced by R1. And if it happens to be the case that R1 is ready, then I'm going to say that all the enable are going to be the enables that come from R1. So the real enable of AM is going to be the one that come from R1. And same thing for all the other signals. Okay? But if it's not the case, then it doesn't mean that actually the enable signal of AM is 0. It could still be the case that it's enabled by someone that comes after it. Okay? So think of it like even though the schedule is R1 before R2, it could be the case that actually R1 cannot go this cycle because another resource is not available this cycle, so then R2 can go. Okay? So you basically go through the set of rules, and for every single rules, you say, is it the case that this rule can go right now? If this rule can go right now, then it means that it's the one that is winning the race of access to the resources. And then, if it is the case that it cannot go right now, then it means that the later rule might be able to go, and then the later rule can go if it's compatible with the previous rule. So in that situation, if it is the case that R2 is not ready, then I try to say, is it the case that R2 is ready? And if it is the case that R2 is ready, then I return the enable of R2, okay? And then, if it is the case that neither ones are enabled, then I say that I don't have this, okay? So you can basically have a sort of scheduling circuitry that goes in order through all the rules and methods of your system, and that look at all the things that can go on right now, because all the resources are ready, and if they can go on, then you make them be the one that win the race and be the ones that drive the signals for that submodules. And then if you have a situation in which actually this one were incompatible, that is here you had a conflict, then in the case where R1 is not ready, so how do I go about that? You could still go later, right? It's just important that you don't set you don't let R2 go ever if R1 goes. Okay? So you basically go through all the rules and you simply thread the signal to say, is it the case that this will want to go? Yes, it wants to go. Okay, if it wants to go, what would it touch? Is it a problem? Would it violate any constraint of the sequential semantic? If it does not, then you let that one go by making that rule signals be the signals for the submodules. If that's not the case, then it's not the signal of the submodules, and you go to the next one, and so on and so forth. Okay? So that should be giving you of an idea of how you can go about that. We actually have a description of this compilation scheme in different places. One is in a PLDI 2020 paper. There is a fairly simple compilation scheme, which we have proven correct, that you can take a look at. And there are also, in actually the reference manual of the BlueSpec programming language, there is a fairly good description of scheduling, which is 15 pages or so. So might be worth to take a look at. Okay, so that's what I wanted to tell you about this compilation to circuits. So basically, recursively, you go up the stack and you create the ready and enable for the parents from the ready and enable for the child, and then you can go up like this. And it actually creates fairly good circuitry. That is, we have written significantly sized designs, and they perform very competitively. So you can actually write program in that language. Okay, so now I want to tell you a little bit more about the second part, which is giving you an example of a simulation relation, because I gave you the definition yesterday, and I also gave you a primer again today. But I think that some people didn't get enough experience with just the definition, so let's look at a concrete example. So we are going to retake our example from yesterday. Maybe it's too complicated. Now let me do a simpler example. So system 1 is going to be your one element queue. So implementation is going to be the one element queue from yesterday. And if you remember, it was simply a thing in which, a module in which there was two registers, one valid and one data. And we had written a little piece of code to describe that if valid is 1, then you cannot enqueue in it. If valid is 0, then you can enqueue in it, and then you can set the valid, and so on and so forth. Okay? So you remember that example, it's just a one element queue. And on the other side, we are going to take the list-based queue, which was the exercise left to the reader yesterday, if I remember, list-based queue. And so here, the internal state is just a list of some type n. And then the transitions are simply, well, if I have a list, then when I want to enqueue in it, and that's basically the answer, then I will get into a state in which I have added the element at the beginning of the list. Then for dequeuing, it needs to be the case that there is an element at the end of the list. And then, so L, and then first it is the case that it returns the first element of the list and I'm going to annotate it with a weird arrow to note that it's a value method. Okay? So notice that here, and it's very common when you do simulation relation. Yesterday, when we wrote the implementation of the one element queue, we wrote it in that little language. I can actually maybe rewrite it to be complete. So it was simply if valid dot read is equal to 0, then we can valid dot write 1, and then data dot write the data, and else abort. Okay? And you can do the same thing for DQ and for first. Okay, so this description is a language description based on the programming language that I wrote on the left, on the right, sorry. And this is a mathematical module in which I just used the ambient logic and mathematics to describe the state transition system. But both of those things have a state transition system associated with them. This one is just directly described as a proposition, and this one is implicitly described by the semantics of the language by composing the transition system of the sub-system, okay? And I want to be able to prove, but the problem, oh, maybe, how do I have this one go up, but this one doesn't go up? Huh. Okay, so I want to prove that there exists phi such that phi exists. Okay, anyone has an idea of what should be the phi? Very easy. So to recapitulate, the state of M is a pair of a valid and a data, and the state of this one is just one element, which is a list. And I'm trying to find a relation between them, which is witnessing the simulation.
It seems to make sense that one element of the relation would be valid is false and data doesn't matter.
Okay, so I like that. So what you're saying is like, I don't know yet how to describe the full relation, but I can tell you at least one point in that relation. And what you're saying is that if valid is false, so false, and then let's write 0. False, and then anything, empty list is in the relation. Right, that's what you're saying. Okay, like that. Okay, anything else? Yes? Let's alternate.
So if valid is true and the list is, yeah, in this case, the list is absent valid.
Okay. 1, 2, 3, 4, 5. Okay. And then, what do we put here?
Yeah, D should have one element.
So here, oh, it has only one element. That's just, it's not a list, this one. It's just one number. So this one should be the same as the one that is inside the list. Okay? Okay, so basically, let's do a wild guess and say that it's actually the relation that is phi of VDL is defined by L equal to empty if and only if V is equal to 0 and L contain one element. So we have a little problem here. What's the problem is we need an existential quantifier. But that's okay. V equal 1 and G equal E. Okay? So that sounds like a reasonable simulation relation to me. Okay. So now how do we prove that this is indeed a simulation relation? And the goal was first to show you something. It's like it's surprisingly painful to come up with that thing. That is, this was completely trivial, right? We just wrote the simplest kind of system with a one element queue and then a two element, an n element queue. And we sort of had to think to find this simulation relation and what's the mapping. And if I had come up with a slightly more complicated example, it would have been harder. And then if I had come up with a non-trivial example like a processor, then it would have been very, very hard to do that. Okay? Yeah?
Is there a reason we wrote it as a conjunction with the quantifier instead of just as a disjunction?
No, you prefer with a disjunction?
I was just wondering if there was...
No. There is no reasons. Yes. Maybe it avoids the quantifiers. You're right. It may be cleaner. So what you're saying is simply I'm saying either v equals 0 or v equal 1, and then you're saying something like L equal empty, and then is it what you're suggesting? Yes, it's better. Avoidance of quantifiers is better. Thank you. Okay? Okay, so now how do we do the proof? Well, we just follow the definition, and basically there is no work to do. It's just algebra, right? Because first we have to prove that the simulation relation holds at the beginning of time. That's fairly straightforward because we didn't specify the empty state, but in the beginning valid is going to be 0 and L is going to be 0, so it's going to be the left-hand side of the relation, the left construct of the OR that is going to hold true. And then, so it is the case that phi of V0, G0, and L0. And then we have to prove that it's inductive. And why is it going to be inductive? Well, let's assume that phi holds for an initial state, so from an arbitrary state. So let's assume that, maybe I should have written it slightly smaller to get more space. Let me put it here. L equal. Okay. And it's really just mechanics at this point. So we said phi of D0, D0, R0, okay. We had not even said what it was, but let's say that we had said it and it was okay. And then let's assume that phi of V, D, L, and we want to prove then if we were to do one step, so we have multiple obligations. First, if we were to do one NQ step, one DQ step, right? We have two obligations. We have to prove that it's preserved by all rules. That's easy because there's no rules in that system. But then we have to prove that it's preserved by every action method, and we have two action methods. So we have two sub-goals. We have to prove that if we start from VD, and we are managing to NQ some elements, let's say E, and we go into some new state, V prime, D prime, then it must be necessarily the case, and we also have phi V. Actually, let me write it as a judgment. This way it will be cleaner. So let's assume we have this, and we have phi V D L. Then we want to prove that we have there exists a state L prime such that coming from L, we can NQ the same element E and land into L prime and phi of V prime, D prime, L prime. Does that statement make sense that this is one of the two cases that we need to prove? Yes?
Just about the relation, if we do the disjunction, shouldn't it be conjunctions inside instead of equivalencies?
Yes. Yeah, you're correct. Yes, I agree. Absolutely. Thank you. I did half of the job of moving to the disjunction. Okay, so that's one case, and we have the similar case in which we replace NQ by DQ. And then we will have to prove the final one, which is if, so we have those two obligations, and then we have to prove that phi implies indistinguishability, and that's an easy exercise. Because if we have, so this is the first goal we will have, and the second goal we will have would be if phi linear, then if we were to observe, so if we were to do VD, then we were to observe calling the first method some return value, then we must be able to prove then that actually there is nothing, it's just that L, if we call the first method, we also get the same return value. Okay? Okay, so how do we go about that? Any guess of what we can do? Yes?
I'm just asking, don't we also need a rule for DQ?
Yes, we do, but it's the same, so let's be lazy. Okay. Oh yes, don't we also need a rule for DQ? That's the question, and the answer is, I just said it. Okay. Okay, how do we go about that? Any clue? Yes? Ah, okay, so you can case on these, that's a good idea. Okay, and what are you gonna get, what are you gonna do? So now we have two subcases. Can we do it in line? Oh, I need to learn how to manage my blackboard. Yeah, let's do it here. Let's erase that. Okay, so now it's easy. We have two sub-goals. So let's consider the case 1D. Actually, yes, this one I love. Okay, so we have this hypothesis now, right? And then we still have phi of 1DL. What can you tell me? Oh, you're going to prove that case. And then below. And I'm not repeating, because actually this case is the easier one. Why is it the easy one? Yes? No? Yes?
If you simplify that, you find that L is less than
Ah, actually, if you simplify phi, so why is it going to be the case that it gives me anything? I don't understand.
because you simplify not phi, but phi of 1D.
Yeah.
L.
But then I'm going to get a 1 equal 1 and something, or 1 equals 0, but that's perfectly okay. Right? It's not a contradiction.
1 equals 0 is not a contradiction.
Well, there's an or. So 1 equals 0 is problematic, but 1 equals 1 on the other side.
You can simplify that expression to find that.
Yes, so you can specify, okay, very good point. Okay, I misunderstood what you said. So what you're saying is that you can simp that thing, and then you're going to get L equal D. Is it what you were saying? Okay, yes, very good. Okay, what else can you do?
Wait, this is the case where an NQ and
Yes. So that's the point, right? This case is absurd. Why is it absurd? Because we are stating as an hypothesis that we are NQing into a full one-element queue.
Yeah.
So if you were to reduce that thing, this is an assumption that you have false here. So false implies anything, so there is nothing to prove here. I mean, there is a very easy proof. Okay? Does it make sense? Okay, so the only interesting case is the case in which you are starting from an empty queue. So now, and that you will see that the reason why we are using proof assistance is because when you do those proofs, you realize that there's a lot of simplification of flowing hypothesis backward, forward, until you sort of can extract all the knowledge that you can from your context. So here, for example, I know that I start in case 0, so I want to be able to say, no, I can symbolically evaluate that thing, and I know that actually necessarily v prime is 1, because I know that the effect of NQing is to go, and there is only one possible new value for v prime, and I know that d prime cannot be anything but the e that is here, because the semantics of NQing is to write to d and to write the value e, okay? And then I can do the trick that was just suggested, which is I can simplify, knowing that now v equals 0, and now I get the fact that L was necessarily equal to empty list before, okay? And now I would need to prove that there exists L prime such that starting from the empty list, if I were to NQ, and then the same element E, I need to prove that I would end up in some L prime such that phi of L prime, and now we know that it's 1E, okay? And that's going to be straightforward by simplifying, by instantiate with L prime. How do I instantiate it with? Yes? Yes. Okay? And then I simplify everything, and then everything works because my relation was chosen to make it work. Okay? So really, in this whole proof, this should all feel like, what have you done? Nothing. The only difficult part was this part. Coming up with this phi, everything else was just mechanics. It was just simplification and unfolding and symbolic evaluation and stuff like this, okay? So I am saying that it's nothing, but mechanically it's a lot of work to make sure that everything works, but conceptually it's no work, okay? Does it make sense? Okay, so I want to give you a slightly more challenging example because we have not done a single example in which we have rules, and I think that something is confusing you with rules potentially. So the example I want to give you is an example in which I actually gave you briefly the example yesterday. It's the f of g pipeline. So the f of g pipeline is the following. Okay. So the f of g pipeline, or implementation, is going to be a system in which we have an enqueue method. Yeah, so very often we have enqueue method and dequeue method. That's very common. And then we have a first observation. Those are because pipeline systems are very common in architecture, and so it's very useful to have this kind of interface. And our specification, so our implementation will have, so enqueue is basically pushing into a little queue. Then there is a rule that pulls from that queue and push into the next queue, and it's composing with F. Then there is another rule that pulls from that queue and push into an output queue. And then the dequeue read from that queue. So 3 queues, and you basically have 2 rules which are pulling from the previous and pushing into the next one. And why is it a design that we call pipeline? Because there might be more than one outstanding token in the system. There might be one previous token flying here and one token there. And the critical path of that system is just going to be the max, that is the frequency at which you can clock this system, is 1 over the max of the length of each of the blocks independently, which is better than the one which we will say is our specification, in which we just have not even a rule, actually. Let's not even do a rule. We will just do, we have 1 queue, and whenever we enqueue, we directly apply g of f when we enqueue, and we push it here. So we sort of, enqueue of x is going to be defined by, if we call this phi for f dot enqueue of g of f of x. And dq read from that one and first. Okay? Yes?
Is that a model or a function?
It doesn't really matter. We can do either way. That's a good question. I don't know. Let's say it's actually written in BlueSpec. That is, let's say that it's actually a program. Yes. I think it's actually a good question in the sense that the fact that it doesn't matter, because when we are going to prove the simulation, fundamentally we are comparing the mathematical object even if it comes from a program. So the only difference is the technical difference of do we have to symbolically evaluate the semantics of the programming language, or is it the case that we already have a closed formula for the relation? But for the definition of for anything inside, it doesn't really matter how we describe the object as long as we describe the same object.
I'm just asking because I'm just trying to see if you're using F to specify like the Q.
Sorry, I see what you're saying. What you're saying is that you're pointing that I'm double using the symbol F on my slide. Okay. This is because this is a Q, and let's call it Q instead of being F. And then that makes much more sense. Sorry, thank you, I didn't catch that. Does it make sense? Okay, so a Q is a submodule, but we name Q F all the time because it's FIFO, and then it gets mixed up. Okay, so I want to claim 2 things. I want to claim that there exists phi such that if I call this I, and then I call it S, then I refine S, but actually, and S refines I. And it happens to be actually the same phi, so we can, it's not necessary that we could also do exist phi for the left side and exist phi for the right side, but it just happens to be that we can prove the same phi. Okay? So now I would like to ask you what's the phi. The reason why I want to ask you what the phi is because in the last lecture, I want us to suffer a little bit through finding the phi, because then we have a technique to not have to suffer. So we have to suffer to not suffer. Okay? So any clue about what could be the phi? So phi, what is it acting on? It's acting on a triple of queues, which is, let's say, the Q1, Q2, Q3. And it's relating that to a single queue, which we will call the QS for the specification Q. Okay? Suggestions? Yes?
Maybe I should, anyone else has.
Anyone else? Do you want to? Ah, yes.
So if you take all the stuff in the, like rightmost queue on the left, and then you put on top of that G of all the stuff in the middlemost queue, and you put on top of that F of G of F of all the stuff in the leftmost queue, it should equal what's in the middle queue on the right.
Excellent. It's exactly the things that I wanted you to get, and more importantly, the intuition, which was put that on top of the previous one, which feels like intuitively what you're saying is like you're sort of right justifying the whole thing. You say push through the thing, and once everything will be pushed to the right, then you would basically say what's there, when there's nothing there, what's there should be the same thing as what's there. Okay? And that's something very easy to write if you're in a higher order logic. Or actually not, but it doesn't require much here. It's simply saying that map of G composed with F to Q1, to which we append map of G to Q2, to which we append Q1, is always going to be equal to QS. Okay? How do we prove that? Well, it's the same things that we just did. We just go through all the cases of our system, except that now we have two cases that we didn't have before, because we have two rules. We have a rule that goes and pull from this one and push into this one, and we have a rule that pull into this one and push into that one. Yes?
Me too, right? The last one?
Yes. Yes. Thank you. Okay. So we want to prove that this is basically an inductive relation. So it's very easy to prove that this, oh, I didn't prove that actually in the previous one, did I? Yes, this one we didn't prove, it was hidden. We didn't prove that phi implied indistinguishability in our previous case. So let's say that we have done it because we will need to redo it now. So let's do it now instead of doing the previous one, okay? So let's assume that this relation holds. Why is it the case that it holds if we try to NQ on both systems? Well, it's gonna hold because if we add a new element here, and we add a new element here, in this new element that we add, we saw in the definition that we directly compose by G of F. So it's going to be, the new state is going to be Q5 G of F of E, right? And the fact that those two equations hold is simply equational reasoning on map and lists, okay? And then you could do the same thing with DQ. If you can DQ, it means that there must have been an element here. And if there must have been an element at the end of that list, because you had an equation that must be that there was also an element at the end of that list, and they are the same one, and then it means that you observe the same on both sides. Okay? And then if you try to look at the case in which you are doing do F or do G, you are going to basically say, if I want to do F, it means that I had one element here that was at the end of that list, and then you are moving that one to there. And when you are moving it to there, the new equation you have will be something like this. Q1 plus plus map of J of, actually, map of J of Q2 F of E concatenated with Q2 plus Q3, right? And that, again, equational reasoning, it's obviously the same. It's just pushing something that was at the end, then bringing it inside, and then pushing it below the G, and then we win. Okay? Does it make some sense? Okay, perfect. So basically, this is the whole rationale of doing proofs in rule-based system. It's basically to simply come up with an implementation and a specification, and then to find a phi that relates them, and then to simply try to prove that this phi is correct. So I want to finish with, in the last 2 minutes, with the most important sort of the hammer that we keep using, and that makes every refinement worth proving, is the fact that refinement is compositional. And it might be obvious to you, but it does require a little bit of work. So what do I mean by refinement is compositional? I mean that let's assume that I have a system M, and inside this system M, I am using a submodule small m. I don't like this letter actually. Let's call it small modules big N. Okay. And then let's assume that I actually know that N refine for some phi another module N prime. So the typical examples that I would give is like, actually we just wrote this f of g pipeline, and we just have proven a refinement on Qs. So if I know that I have a one element Q, which refine my least-based Q, then we have a theorem that states that necessarily using that implementation is going to produce a module, and that module refine for another refinement psi using the implementation. Okay? So what it means is that whenever I want to prove the correctness of a top-level module with a lot of submodules, the first thing I do is I look at the submodules and I say, can I find a better specification for them, which is simpler? I prove the refinement on the submodules. Then I use the refinement theorem to simplify my big module by replacing the submodules by the simpler versions. Then once I replace them by the simpler versions, my proof will be easier because I won't have to consider the technical problems of the more complicated version. So a typical example of that I could give you is, so someone yesterday asked about, okay, you told us about one element Q, but sometimes maybe there are also two element Qs. There is actually k element Qs, and they are not so uncommon. For example, in an Apple M1, there is a 600 element Q. So, you know, better be able to handle that. And if you think about the way it's going to be implemented in hardware, it's going to look like this. It's going to look like you're going to use an array of n registers and then you're going to use an NQ pointer register and a DQ pointer register. And then you're going to have a ring buffer, and that's the way you, in hardware, implement a k element Q. The thing is that if I consider this module, there is actually already n ways to be empty. Right? Because I could be empty with NQ pointer equal DQ pointer equal to 0. I could be empty with NQ pointer equal DQ pointer to 1, to 2, to 3, to 4, to 5, etc., etc. So if I have any property to prove, fundamentally, if I have such an n element Q in my system, I have a system, a group of symmetries of all the symmetries modular rotations that I need to consider in my proof, which is very painful. If I start by saying, actually, I have a proof that this system refines my list-based system, which is a spec on list, then I don't need to ever consider this symmetry of rotations, because in my proof, I only need to consider the case where I have a list of elements. Well, I need to consider something slightly more complicated, because here, maybe it was a 100 element Q. No, it's an infinitely element Q, I mean, unbounded element Q, but at least I don't need to consider the symmetry. So that's one of the key sledgehammer of our methodology, is the fact that once you can figure out nice to work with spec for all your primitive hardware modules, then it eliminates a lot of the cumbersome technical details of low-level hardware, because your model is mass, and you've proven that your mass model is actually a faithful representation of your hardware at a step-by-step. Okay? And that's basically, I think I don't have time today to prove this theorem to you, but fundamentally it's not really hard. Psi is basically going to be a relation which is going to be the equality on all modules, except on the module you are replacing, on which you are going to use the phi that you have. Okay? So it's fairly straightforward. It's a little bit, when you do it in the proof assistant, you know, it's a little bit of suffering, but that's basically expected. Okay? Well, I think that's all for today. Thank you. And tomorrow we will do processor.